platinum catalyst, and he developed the first hydrogen oxygen fuel cell. Now, as of now, after that, like in 1960, fuel cell found application in the US space program. In 1965, it was used in Apollo mission. Okay, they used 3 fuel cells, and the wattage was ranged from 463 to 1463. But if you compare, this technology is so old, but yet it has not gained ground as of today, 2021. So what could be the reason? The reason is that other technologies, cheaper technologies have been available to us. Fuel cell, since it involves, noble catalyst, hydrogen, oxygen, okay, so, and those electrolyte. So, it's an expensive technology. So yeah, to make it, to popularize it, we have to bring down the cost. Okay, and we should make the the components of the fuel cell easily available, easily procurable. But since there are other technologies which are much cheaper and easier to generate energy, so this fuel cell was at the backseat till few years back. But now we are depleting our fossil fuel resources. We are looking for alternatives. So now this technology is gaining ground, and researchers have proven that this technology really has potential, okay, either as a standalone system, maybe, and as you all know, by automotive applications also, it fuel cell cars and fuel cell buses have been developed and commercialized, right? So the basic components of fuel cell is very much like a battery. As a battery has 2 electrodes, one anode and a cathode, the fuel cell also has an anode and a cathode, and this has the electrodes have to be conductive, so they can be of metal, nickel, graphite, carbon nanotubes. Now, at both the anode and the cathode, 2 types of reactions will take place. At the anode, oxidation reaction takes place, and at the cathode, reduction reaction takes place. Now we know that to support any chemical reaction or any biological reaction, we require catalyst. So in a fuel cell, we can either use a chemical catalyst or we can use a biological catalyst. Say, for instance, platinum is a chemical catalyst. So what do we say? That is a chemical fuel cell. Now suppose instead of platinum, we use microbes or enzymes. What are these? Are biological catalysts. Then we refer to that type of fuel cell as biological fuel cell, microbial fuel cell or enzymatic fuel cell. Now both this anode and cathode has an electrolyte in between them, okay, and that is to facilitate ionic conduction. Now this electrolyte can be a polymer membrane or can be made of ceramic also, okay, that will come later on. And fuel, what type of fuel can we use in a fuel cell? In fact, any fuel which contains carbohydrate, okay, can be used as a fuel in a fuel cell. Say hydrogen, alcohol, say methanol, ethanol, wastewater, because they are rich in carbohydrates, glucose, cellulosic substances, anything can serve as a fuel in a fuel cell. Got it? So this is just to show how a fuel cell works. Okay, so see, this is the anode, this is the cathode. Now, either we can directly say, if we use platinum as the anode and platinum as the cathode, it serves the purpose of electrode also because it is electronically conductive. Also, it can support oxidation reaction and reduction reaction. So it acts as a catalyst also. But if you want to use, say, some other electrode which cannot support oxidation and reduction reaction, in that case we have to apply catalyst. Okay. Now in this fuel cell, say we are using platinum as the anode electrode or catalyst, platinum as the cathode catalyst. In between there is a proton exchange membrane. Now let me tell you, this proton exchange membrane is negatively charged. Why? Because, or so that the fuel, say in this case we are introducing hydrogen. So platinum has the capability to oxidize hydrogen. Now since our school days we have been learning that during oxidation electron is generated, right? Now we want to harness this electron for electricity generation. Now if this proton exchange membrane had been positively charged. From the anode to the cathode, the electrons could have easily passed. So we would not have been able to harness the electron for power generation or for current generation. So what is the primary requirement? This your proton exchange membrane or electrolyte has to be negatively charged. Anode catalyst, cathode catalyst, proton exchange membrane or electrolyte, which is negatively charged. So when hydrogen is oxidized at the anode, two things are generated. One is the proton and one is the electron. Now, since this membrane is negatively charged, electrons cannot pass through this. Okay, so we provide an external circuit. In between, we provide the load and we harness electricity. And the protons, which are positively charged, can easily reach the cathode catalyst through this electrolyte. So at the cathode, the electrons, okay, from by this external circuit, the protons through this proton exchange membrane, oxygen from the atmosphere, or maybe we can use pure oxygen cylinders also, okay, they undergo reduction reaction. And what we get as the product, we get heated water, okay, since it is an exothermic reaction. Now, another important thing of fuel cell is that as oxidation takes place at the anode, so the anode electrode is negatively charged and the cathode electrode is positively charged. And another most important is that always remember that a fuel cell to perform efficiently, the anode chamber must always be maintained at anaerobic condition. Okay, why? Because if it is aerobic, if we keep the anode chamber aerobic, oxygen is a very good acceptor of electron. So whatever electrons are generated because of oxidation will be captured or quenched by this oxygen. So you would not have free electrons, okay, to produce electricity. So always we have to make sure that the energetic chamber of a fuel cell is maintained at strict anaerobic condition. Got it? So what happens? What are the reactions that take place at the anode? At the anode, say our fuel is hydrogen. Oxidation takes place. So oxidation breaks down into protons and electrons. At the cathode, reduction reaction takes place. And what are the reactants of reduction reaction? Oxygen from the atmosphere, the protons, which we get from the anode oxidation, the electrons, which we get after passing through the external circuit, and ultimately they are reduced to form water. So the overall reaction is hydrogen and oxygen will give water. So this is just the reverse of electrolysis, right? So here schematically I have shown like how it is. This we call, three electrode assembly or three-phase assembly. Anode, electrolyte, cathode, and they have to be close together to avoid resistance, internal resistance, okay, which will again decrease the efficiency of the fuel cell, okay. So, and that is a hydrogen oxygen fuel cell we discussed, and this is a biological fuel cell. So what will be the fuel in a biological fuel cell? The fuel may be any organic matter, maybe cow dung, maybe wastewater, it can be anything, okay, maybe organic biomasses, okay, it can be any carbohydrate containing matter. And we know that since it contains carbohydrate containing matter, okay, and it needs to be oxidized. Now, we know that microorganisms can easily oxidize the waste matter. So what we do for biological fuel cell, we use microorganisms as the catalyst. Okay, so anode, maybe anything, maybe a carbon cloth, maybe a carbon rod, or maybe a graphite rod, any electron conducting surface can serve as the electrode, anode electrode. And what will be the catalyst? The catalyst can be directly the whole organism, microorganism, or we can extract the enzymes from the organisms and immobilize on the anode, okay, and then use it as the anode catalyst. But that involves cost, okay, because our target is to reduce the cost of fuel cell performance. That is why rather than going to enzyme, it is better we use microorganisms because any type of microorganisms we'll get just from a cup of wastewater. Okay, we'll have millions and millions of microorganisms, okay, which can be used as catalyst for generating electricity from our wastewater. right? So other arrangements are similar. We keep an electrolyte in between to facilitate the migration of proton from anode to the cathode. Now at the cathode, this is the load we are introducing. Then at the cathode, the electrons from oxidation of waste biomass, okay, the protons, and as you can see, the cathodic chamber is aerobic. That means we have to introduce oxygen. It can be either atmospheric oxygen, and if you want to reduce the cost, obviously you're not going to go for pure oxygen. You don't require 99.9% oxygen. Aerobic oxygen is sufficient to serve your purpose, okay? So this is briefly about the electrolyte. As I discussed in the second slide, the electrolyte can be ceramic or it can be polymer. Usually the state-of-the-art electrolyte for fuel cell is developed or produced commercially by DuPont. It is known as Nafion, which is a perfluorosulfonic acid membrane. This is the chemical structure. As you can see, it has carbon and fluoride backbone. This is hydrophobic in nature. It has a side chain ending in a sulfonic acid group. This sulfonic acid group has a negative charge, okay, and this imparts a hydrophilic nature to the membrane. Now, the most important thing that we should remember while using the Nafion membrane is that at all conditions, to perform at its optimum level, the Nafion membrane must be 100% hydrated. Why? Because, see, this is the electrolyte. It should facilitate crossover of proton from the anode to the cathode. Now, in the presence of when the membrane is hydrated, what happens, since it contains hydrophilic groups and hydrophobic backbone, so in the presence of your water, it forms hydrophilic pockets of sulfonic acid sites like this, okay? So whatever protons are generated at the anode electrode because of oxidation will, jump from anode to the cathode side through hopping mechanism. They will jump from one hydrophilic pocket to another hydrophilic pocket and ultimately reach the cathode side where they will be eventually reduced, okay? But if we say increase the temperature or dehydrate this electrolyte, okay, what will happen? There will be discontinuity of these pockets, okay, and that will break the passage of proton migration and your fuel cell efficiency will decrease, right? So this is another, important component of fuel cell, which is very costly, and world over, researchers are trying to, lower the cost of fabricating alternative to Nafion membrane. But as of now, they have not been able to synthesize any membrane which performs or whose performance is at par with Nafion membrane. Okay. Now this is the we have the anode, we have the cathode, we have the electrolyte. Now how to assemble all this to make a complete fuel cell? Okay. So see, this is the schematic. Say this is the anode. Okay, this is the electrode. Okay, this is the electrode. This will be the anode, this will be the cathode, and this is your white piece, your electrolyte. Now, we require, gas diffusion layer because we are going to, in case of chemical fuel cell, we use hydrogen and oxygen, right? In case of biological fuel cell, it is different. So, in case for our hydrogen fuel cell or chemical fuel cell, we are using a gas, we require gas diffusion layer so that, all part of your catalyst uniformly, is in contact with the introduced gas. So this is, as I already said, this is a three-phase assembly: anode, electrolyte, cathode. Okay, and this is also referred to as membrane electrode assembly. Now here you can see I have made a membrane electrode assembly by compressing it, because the more compressed it is, the better will be your performance. If there is an air layer in between, that will increase the resistance, internal resistance, and that will decrease your fuel cell efficiency. Got it? So this is the membrane electrode assembly. This side you have the anode, on the other side you have the cathode, and your polymer electrolyte membrane is sandwiched in between. So this is a compact system, membrane electrode assembly. and now you want some accessories. Okay, so this is the accessory, say of one side. Maybe this is, say, these are these are what channels. Okay, through this maybe you introduce your hydrogen or methanol. They will pass through these channels. Okay, and whatever waste or after reaction, whatever byproduct that will come out from this. This is one side of your fuel cell. On top of it, you are going to place this membrane electrode assembly and cover the other side with a similar bipolar plate. These are known as bipolar plate. Okay, and you have, and then you adjust it or tighten it with screws and gaskets. Okay, then these are the gold current collectors. You can, for experimental purpose, it will be something. This is a very rugged thing. This is for experimental purpose. Obviously, if you are manufacturing, it has to be very refined. Okay, so your design has to be very defined. So this is a single stack, right? And if you want to increase your voltage, you have to connect in series or parallel so that you meet your requirement. Because when you connect a number of stacks, or when you do stacking, you will be able to increase your output voltage, which is DC. Okay, direct current. So as I said, a fuel cell is very much like a battery, but it is not a battery because a fuel cell does not store energy. Okay, a battery, like a battery has all its chemical stored within this container, which goes oxidation and reduction reactions, continuously. And maybe after some time, when it gets exhausted, then we say the battery is dead, and we replace it with another battery. But the same is not the case with fuel cell. A fuel cell has the components intact, and as long as you keep on supplying your fuel, the fuel cell will keep you giving electricity. Okay, or will keep giving or keep performing, right? And another thing is that in a battery, the electrodes, they react and they change. Okay, the composition changes over time. But as I already said, in a fuel cell, the electrodes can also act as the catalyst. Okay, if it is not a biological fuel cell, or maybe if you are not using platinum, okay, or some other metal which can act as catalyst. So as you know, the catalyst does not get used up in a reaction. So doesn't matter how old is the fuel cell, the catalyst will remain as such. Got it? So that is the difference between a fuel cell and a battery. And here you can see several stacks of fuel cells, they are placed in series to make, this will have a very high voltage output. So this is actually about an hydrogen oxygen fuel cell. As you can see, like compared to since fuel cell does not involve combustion, okay, so it directly, but it is referred to as electrochemical reaction, because chemical energy is converted to electrical energy. So there is no combustion involved, so its efficiency is high. Okay. Similarly, it does not have any moving part. Okay. So obviously, its longevity will be better than your combustion engines. Then byproducts are produced like NOx, SOx compared to combustion engines. But the main hurdle is cost. As I already discussed, the electrodes, which if you need them to perform as a catalyst, the platinum, that is very expensive. Now, second is the proton exchange membrane, that is also very expensive. Now we are talking about using hydrogen. Now you know that hydrogen production storage is an issue, right? Then and if you are planning to use it for, say, transportation purpose, then that stop-start cycle, that takes time. Some issues are there. Okay, so like to address these issues, the biologists or the biological researchers, they try to replace the chemical catalyst with biological catalyst. In fact, they have achieved much success, but I wouldn't say that this success is in terms of power generation, but rather in terms of other things. Okay, I will discuss about that. Okay, let's see. Okay, another thing, as I said, please see here that maximum efficiency of a fuel cell is calculated to be, say, 83%. Okay, but that is not so. Why? Because losses are incurred at several steps, which is known as in the overvoltage. So let's see what are the different steps at which the fuels or which decreases the fuel cell efficiency. The first is referred to as activation losses, which is because of the slow reaction kinetics. To start the reaction or how to drive the reaction, it takes time. Okay, and in fact, the initial electrons that are generated because of oxidation, they're from them or they cannot be utilized for harnessing of electricity because they are required for driving the reaction. Okay, that is referred to as your activation losses, and that is incurred at the initial stage, right? You read about this in chemistry, if you remember, right? So the next is that ohmic losses. Those are the resistances offered by the anode, the cathode, the electrolyte, the different accessories of the fuel cell. And the last is, in fact, the mass transfer losses, which is because it is seen that when we increase the current density, usually the amount of reactance over the electrode, okay, that is not at its optimum. Okay, that is referred to your mass transfer losses. Okay, and another thing that is fuel crossover losses. This does not apply to all types of fuel cells. In fact, if you're using a liquid fuel, say for instance, if you're instead of hydrogen, if you're using methanol, okay, now methanol can pass through this membrane, your electrolyte membrane. Now you are using platinum on the anode side also, you are using platinum on the cathode side also. Now what happens? Platinum has the ability to oxidize methanol. So electrons will be generated at the anode. Now these electrons you can use for harnessing electricity. But what will happen to the methanol which crosses over through the membrane and reaches the cathode? There also the methanol will be oxidized. Electrons will be generated. But will you be able to use that electrons? No. In fact, that is going to reduce your performance of your fuel cell. So that is the loss due to fuel crossover. Okay. So this is some thing that has been discussed in reference to your chemical fuel cell. But obviously activation losses, ohmic losses, concentration losses will be there for biological fuel cells also. Okay. So this is some steady state output of our fuel cell. It shows that if we keep on increasing the fuel input, the performance of the fuel cell also improves. But again, what we have to increase the reaction kinetics at the anode, the reaction kinetics at the cathode. So a lot of researchers are going on development of catalyst also. In fact, researchers are going on every component of the fuel cell. Some are trying to increase its efficiency. Some are trying to use alternative material to decrease the cost of the fuel cell to popularize the technology. So if you browse through literature, you will find researchers are full-fledged on every aspect of your fuel cell. Okay, power in terms of power density, as you can see, that fuel cell low volumetric power density as compared to combustion engines and batteries. Nevertheless, it's almost comparable, right? Because if we consider the environmental impacts, okay, so fuel cell will obviously be a better option in the long run. Okay, now briefly about the types of fuel cells. I already said that fuel cells on the basis of catalyst, they can be chemical fuel cell or biological fuel cells. Similarly, on the basis of what type of electrolyte you are using, they can be polymer membrane fuel cell. If you are using phosphoric acid, it is a phosphoric acid fuel cell. If you are using, say, potassium hydroxide, okay, as the electrolyte, so that will be known as an alkaline fuel cell. If you are using molten carbonate as the electrolyte, that will be referred to as molten carbonate fuel cell. If you are using ceramic, that will be referred to as solid oxide fuel cell, right? But as you can see, the charge carrier is either protons, or maybe in case of potassium hydroxide, it is hydroxyl group. In case of molten carbonate, this is the ion, okay, which will pass from the anode to the cathode, right? And in case of ceramic, this atom ions. So as you can see, the operating temperature also varies for proton exchange membrane fuel cell, where fuel is usually hydrogen or methanol. The optimum operating temperature is 80 degrees centigrade. We cannot go beyond that. Why? Because I already discussed this membrane, polymer membrane, needs to be in hydrated condition. If you go beyond 80, they will slowly start losing water, which will what? decrease the performance, disrupt the hydrophilic channels, and will decrease the performance of your electrolyte. So your fuel cell efficiency is going to decrease. So these are known as moderate temperature fuel cells, say 200 or 60 to 200 degrees centigrade, and these are high temperature fuel cells. Solid oxide fuel cell are high temperature fuel cells, and they're usually used for standalone purposes. Okay, but if we talk about hydrogen or methanol to be used as fuel, usually we go for the polymer membrane fuel cell. In fact, for biological fuel cell also, we are going to use polymer membrane only. In some cases, you can use some biological fuel cells do not use membranes, because this separation of anode and cathode through this aqueous layer itself, that serves as the electrolyte. Okay, so efficiency, as you can see, ranges between 35 to 60% in most cases. So a lot of work is still there to increase the efficiency of fuel cells. Cost is still very high. We need to reduce the cost, right? And size is, as you can see, this is this unit size. Okay, so and as regards to biological fuel cell, since that will be the topic of our discussion. So you can use either direct enzymes or microbes. Okay, the whole organism. But as I said, our aim is to decrease the cost of the fuel cell and the performance of the fuel cell, the sustainability of the fuel cell. That's why we are going to go for microbes and not for enzymes. Okay. So biological fuel cells can be used for conversion of organic biomass to energy. How? See, this is a schematic of a biological fuel cell. Okay, this is the anode, this is the cathode. Anode, whether it's a biological fuel cell, whether it's a chemical fuel cell, anode always has to be in anaerobic condition. So whatever microorganisms you are going to use, those have to be anaerobic microbes, okay, which can survive in the absence of oxygen. Got it? So see, this chamber, anaerobic chamber, is quite large because you will introduce, in this case they are showing glucose, but we can use wastewater or any carbohydrate containing substrate which has to be not in solid condition. It has to be, because the microbes, they require water, presence of water to perform at their optimum. They cannot function in dry conditions, right? So it has to be watery, maybe 1:1 ratio. Okay, cow dung is to water, 1:1 ratio. That can also serve as your fuel, biological fuel. And you can use glucose, you can use wastewater, you can use sewage waste, anything you can use, because these contain what? Carbohydrate. This also has microbes in them, right? So when you introduce them in an anaerobic chamber like this, and you have an electrode, any electron conducting surface, say in this case it is a carbon cloth or carbon rod, okay, that can also serve as your anode electrode. And so what happens? Your microbes will oxidize the carbohydrate which are present in the waste, okay, biomass waste. So as your oxidation involves generation of electrons and protons, these electrons will be captured by this electron conducting surface. So it will take to the through the external circuit where you can harness this for electricity generation. It is going to reach the cathode side. It is going to reach the cathode side through this external circuit, right? And at the cathode side, you have to have an electrode which supports reduction reaction. You can use enzymes also if you want, but usually we go for graphite because graphite can reduce oxygen. Okay, so at the cathode side, we introduce oxygen. So these protons come from anode to the cathode side, the electrons through the external circuit, and ultimately what you get? Water. The cathode performance is very similar to your chemical fuel cell. Anode performance also similar, but as you can see, this anode chamber volume has to be high because you are going to introduce, the COD value has to be high. Otherwise, how it will be, you have to sustain the growth of the microorganisms. Okay, and for the growth only, we are going to oxidize this carbohydrate, and this oxidation is going to generate electrons, which you are going to harness for, electricity generation. At the same time, what is happening? your microbes are also helping to bioremediate your waste, right? It is reducing your COD value. Okay, so these are two things that are taking place simultaneously. But usually it is observed that the electricity that is generated from, say, biological fuel cell is very less, right? We are not able to, in fact, light a bulb. But does that mean that this technology does not have any, future or any scope? No, that is not the case. Other things have come up, okay? Because if we fail at one thing, if you keep on performing, obviously something or the other is going to come up. And what the researchers have discovered, that this microbial fuel cell can be used for, generation of hydrogen, can be used for generation of methane. Okay, although we used anaerobic digesters, but anaerobic digesters are again having several limitations. Say the performance decreases in cold conditions, but that won't be the case when we are talking about fuel cell. Similarly, this microbial fuel cells, also enzymatic fuel cells, can be used as biosensors. Okay, and they can also be used for production of chemicals. So this fuel cell technology only. It's a fuel cell applying the fuel cell technology only. These are the different things which you can generate. Okay, so now researchers are diverting their they are not only limited to electricity generation, but they are also diverted to hydrogen production, methane production. So these can be utilized for energy production. Okay, so and another thing, I just forgot now. If it comes to my mind, I'm going to share with you all. Okay, let's see. Next. Oh yeah, another thing. Another thing, researchers have realized that when we are using biological fuel cell for electricity generation, we should always try to, use a power management system. So with the help of a power management system, which is also an area of research of my lab at present. So even we are able to increase its power output. So we all can target, okay, to use a power management system for enhancing the electricity generation with applying biological fuel cell. So okay, about when we say chemical and the reactions are there, so it becomes very easy for us to understand how the electrons are transferred from this hydrogen to your electrode. But how are electrons transferred from the microbes to the electrodes? Well, there are three types of mechanisms that have been identified. One mechanism says that some microbes, okay, they have the capacity to form a film on top of the electrode, as they can directly transfer the electron to the electrode. That is referred to as direct contact. Now, scientists or researchers have also identified microorganisms which produce such type of wires, which are known as nanowires. Now they are highly conductive. Okay, this is an integral part of the microorganism, and they help to transfer the electron from the microbes to the electrode. And the third type of microbes, they release some mediators, which are usually proteinous in nature. What these mediators do, they collect the electrons from the microbe and then transfer them to the electrode. So these are the three types of mechanisms that have been identified for transfer of microbes to, for transfer of electrons from microbes to the electrode surface. Got it? Okay, so these are some evidence of microorganisms capable of producing nanowires. You can see this. These are nanowires. Okay, so this is the microbacterium. So what do they do? They oxidize carbohydrate containing substrates. Electrons are generated. These electrons find their way through the nanowires to the electrode. So once they reach the electrode, obviously they move out to the external circuit, and we can harness electricity from it, right? Now, this is a schematic diagram where I want to show that why our anodic chamber should be anaerobic, that is devoid of oxygen. Because see, this shows here, in the presence of oxygen, what happens? See, why do we perform respiration? We perform respiration to get energy from our food. Right? We take in oxygen, then that oxygen oxidizes, electrons are generated, carbon dioxide is generated, right? And ultimately, I'm not going to go into detail that electron transport chain is there, ATP is generated, we get energy. This is in the presence of oxygen. So if we make the anaerobic chamber, the anode chamber aerobic, all our electrons which will be generated because of oxidation of your carbohydrate waste will be captured by the oxygen. So to prevent that, what is done? We make it anaerobic. Now when we make it anaerobic, see, the microbe gets food, the food gets oxidized, electrons are generated, they search for oxygen to donate their electrons, because they have to donate the electron to get energy so that they can proliferate. Okay, they can get energy to proliferate. Okay, they have to remove these electrons from them. So what happens if we maintain an anaerobic condition, and this is an electron collector, anode. So what happens? The electron comes out and gets deposited on the anode of your fuel cell, right? So that is why we have to make sure that the anodic chamber of a fuel cell should always be maintained in an anaerobic condition. Got it? Okay. Excuse me. So this shows a schematic of our fuel cell. Here, see, this is the anode chamber, this is the cathode chamber, this is the proton exchange membrane, this is the fuel, which is usually waste. Okay, these are the microbes which form biofilm on the electrode. Maybe this is a, say, carbon paper. They form a biofilm. They oxidize the waste. Electrons are generated. Electrons facilitated through an external circuit. We harness electricity. It comes to the cathode. Protons, they do not go through the external circuit. Easily they can come to the cathode through this proton exchange membrane because it is negatively charged. At the cathode, we introduce oxygen. Okay, so oxygen, electron, protons, they undergo reduction reaction, and they ultimately we get product as water. So this is a simple setup, experimental setup of a microbial fuel cell. Okay, this is the anode, this is the cathode, this is the proton exchange membrane. Got it? Now, see, as I said, biological fuel cell has many applications. One is for electricity generation, though less, but still it has applications. It can be used for generation of methane. It can be used for generation of hydrogen. It can be used for, developmental biosensor. Okay, so let's see how biological fuel cell can be used for electricity generation. Now, these are the various, substrates. Okay, biological substrates which can be used for, in fuel cell. But it's not restricted to this. Okay, we can keep on increasing the list. Okay. Because I work on anaerobic systems, I see cow dung missing in this slide. So we can use cow dung also as a fuel for biological fuel cell. We can generate electricity from cow dung in a similar way also. So you can see the substrate and the power generation capacity per meter square. And this is a simple fuel cell. This is the excuse me. This is the anodic chamber. And see, this cathode is known as air-breathed cathode. The anodic chamber, in between there will be a membrane, and on top of it there will be a, say, graphite paper to to support reduction reaction. Now this is highly porous, so it will take air from the or oxygen from the atmosphere, and it will support the reduction reaction. This is a single stack biological fuel cell. Okay, this is a different type of design. Now see, we know that in US and all they treat wastewater, right? Here also, like that, the culture has come that okay, we can reuse wastewater. In fact, it is said that domestic wastewater has 9.3 times more energy than the energy it consumes during its treatment. So it is very justifiable that we use wastewater for electricity generation for its own treatment. Okay, then we don't have to depend on external energy source, right? So that way we are going to generate also electricity, and similarly we can use it for its regeneration of water also. But the technology has to be developed. As I said, the cost has to be reduced, and for that we need to give our input. Okay, we all have to come together. Biologists have to come together for addressing the biological issues. mechanical engineers, you have to come, to look into the design part, because you see, it is said that it is not the process which has limitations. It is the design of the fuel cell which has limitations. We will show in the next slide also how it is. Okay, now see, as I already said, that why do we eat food or why do we oxidize food? To get energy. Similarly, bacteria or microbes, they respire to get energy so they can proliferate, they can multiply. So this is just to show that only. Yeah, I have picturized it. Okay, now see. This is electrical power generation in the microbial fuel cell using exoelectrogenic microorganisms. We already talked about this, but here one difference is there. See, they have not used a proton exchange membrane. They have just distanced the anode and the cathode. So this contains your wastewater. So this acts as your electrolyte. But it has to be highly conductive. Again, otherwise what will happen, its performance is going to decrease. So in this case, for this case, we need to make this liquid highly conductive, right? Otherwise, the protons will, there will be limitation of the protons reaching the cathode side. So which is again going to limit your power production. So as I already said, this is an air-breathed cathode. This is the anodic chamber, and these are the various components with which this is fabricated. Okay. Now, this is a repetition of that only. Okay, without. Okay. Now, okay. Now we know that wastewater can be acidic or wastewater can be neutral. But as this slide shows, that whatever be the wastewater, okay, those type of wastewaters will have microorganisms which can survive in that condition. Okay, we need not bring microbes from some other source. We'll have the microbes in that wastewater itself, which can, survive and multiply in that condition only. What we need to do, we need to collect them, and we need to, culture them in the fuel cell conditions. Then only we will be able to use different types of, waste, whether acidic or neutral or basic, okay, for electricity generation. That is what is tried to show in this slide. So whether it's acidic condition or neutral, but we can use all types of wastewater for electricity generation. And second is that along with electricity generation, when we use wastewater in a fuel cell, the simultaneous activity that takes place is reduction of COD value or biodegradable percentage. Okay, so it also bioremediates at the same time. Got it? This is the current level of development of biological fuel cell. This is the raw laboratory scale method. Now this is highly emerged method. Okay. Now see, this is clearly stated that it is a system architecture, but not the microbiology which limits power. So if biologists and mechanical engineer who have idea about designing or how to reduce the resistance, the efficiency of the fuel cell can be improved immensely. So that is why centers have come up and interdisciplinary researchers have come up. So everybody can contribute what they know, so that ultimately the product. Now, like these days, people don't works independently. Okay, you'll be that way. You'll be slowed down. Your pace will be slowed down. Everybody has to come together. Okay, and main thing is that it should be a win-win situation for all. Generally, everybody feels like contributing. If one only takes the credit, obviously, who is going to collaborate, right? So we should collaborate, and the coordinator should be such that he should facilitate, a win-win situation for all the collaborators. Okay, then only the group can actually emerge. Okay, so this is the slide which I wanted to show. So this is the very raw design. Just see, you get 0.3 to 3 milliwatt per meter square, and the system resistance is offering 66,920 ohms. On the other hand, you just change the design a bit. Say instead of, because you're using bottle, and using instead of using pipes, this type of thing, you are using bridges like this. You're capping it. Resistance decreased from 66,920 to 1,750 ohms. Got it? And the power increased from 3 milliwatt maximum to 4 milliwatt per meter square. So similarly, by improving the system design, we can also improve the power. Okay. And second, power management is obviously very necessary, because chemical, obviously microbes won't have, the reaction kinetics will be slower than a chemical catalyst, right? So the practical barriers to commercialization or popularization of biological fuel cell is low electricity production, the current instability, and high internal resistance. Okay, obviously high operating cost, low power output is because of these reasons, and the high cost, as I said, we use proton exchange membrane, which is usually Nafion, the different parts, okay, which are made of plexiglass and all, and that increases the cost. And researchers are trying to decrease it by replacing with alternatives, but still there's a long way to go. Okay, so now real applications of microbial fuel cells are limited due to the low power density level of only, I think we are getting 1000 milliwatt per meter square. So obviously by stacking it, this can be increased, but stacking can, we cannot keep on indefinite. Stacking is not possible. Only maybe 40 or so we can stack it, or otherwise, this reverse potential that takes place, and your entire fuel cell performance decreases. Okay, so a lot of design improvement is required in case of biological fuel cells. So this is a system scale up. So instead of flat anodes, they are using brush anodes, and instead of using rod or flat surface cathodes, they are using tube cathodes. And this is 3-stack assembly: first stack, second stack, third stack. So similarly, by increasing the stack, we can use the power output. Okay. So many researchers, they have tried to use activated carbon as cathode, and they have been able to get good results. And they have also, since we know that cathode has to be perforated to allow airflow or oxygen flow, but it is seen that 70% when the porosity is 70%, then this is the power output they are getting, which gradually decreases to almost similar. And this has got a slightly lower, initial slightly lower power density, but again it reaches almost similar. So the reason for this, they are saying, is that with time, what happens, as I said, when we are using a microbial fuel cell or a biological fuel cell, they form a layer, a biofilm. Okay, so because of the formation of this biofilm, the electrons cannot reach the electrodes. So we need to clean it, or we need to replace it. Now, if you replace it, again, that is going to increase the cost, right? Because this is going to cost us. But if we clean it, I think that is slightly going to, decrease our cost. But at the same time, as you can see here, cleaning slightly increases the performance, but the performance is not at par with a new one. So these are certain things. We can also start working on, cathodes, okay, to replace in biological fuel cells. So this shows the performance of a new cathode. After 1 year, the performance decreases. This is because of the biofilm formation. The electrons cannot reach the cathode. After cleaning, what happens? Slightly the performance increases. And when we introduce a new one, it almost at par with the initial new cathode. Okay. So we need, methods to maintain the anode cathode catalytic activity. And for that, we have been trying to use, alternatives, or searching for alternatives. Okay, so if by changing, making some changes, we are able to get slightly higher, that is reported and accepted. Maybe that way at one time. Okay, maybe it's something like lithium-ion batteries only. Like it started way back. Now the researcher has been awarded a Nobel Prize, after so many years of research. So similarly, maybe if you all start working from now, maybe it will take 50 years or so to actually make it, practicable. So this is a picture of a sediment fuel cell. Sediment fuel cells are biological fuel cells only. So see, this is the anode part. This contains sediments, pond sediments. It can be anything. Drain sediments. It can be anything. Okay. It contains what? Carbohydrates. Okay. So the anode is kept submerged here, so that an anaerobic condition is maintained, and the cathode, okay, is kept somewhere near the surface layer, so that it can come in contact with the atmosphere, so that an anaerobic condition is maintained. So this is, we actually try to create an anaerobic anode by introducing aquatic aquatic weeds. Okay, we could get some good results, but as I said, power management system is required to actually make it practicable. So say for instance, this is blank. This had no carbohydrate containing, but see, as soon as we introduced waste slurry, the power it increases. The voltage increased from 0.249 to 0.576. Got it? So this is something, utilization of microbial fuel cell for using toilet for energy generation. So as you can see, this is a single unit. They have used what? Tube cathode. This is a cathode tube. On top of it is the membrane surrounding it. It's a ceramic membrane. On top of it will be your anode. It's a cylindrical type of thing. One will insert into the other. Okay, and this whole system is inserted into a cylindrical tube like this, where we introduce the urine. Okay, and plug it. Okay, and the cathode is so arranged that it will be in contact with the outer surface for maintaining an aerobic condition, and they have designs such trays where they can take around 560 units or so. So this has been successful, okay, for generation of power, okay. And these are something like tubs, terracotta tubs, what we use for plantation and all, for potted plants and all. Such type of designs have also come up. Usually these are for utilization of wastewater or maybe toilet waste. We can use it. But people, they are not ready to work with cow dung only. Human waste to leave alone. It will take a long time for us to accept this, right, for power generation. Similarly, as I said, that since biological fuel cell, the power generation is so low, so like researchers have found that biological fuel cell also can be used for hydrogen production and methane production. Let's see how. See, current source of hydrogen is what? Electrolysis, which gives around 4%, natural gas 48%, heavy oil and naphtha, we get around 30% hydrogen from there, right? Coal 18%. Now from glucose also, we can generate hydrogen, that is by fermentation, and usually glucose is used for generation of ethanol. Okay, we get only 2 ethanol from glucose per glucose molecule, and we can get about 12 hydrogen molecule per glucose molecule. Okay. So, but as per DOE target, they are trying to use technology to get 10 to 12 mole of hydrogen per mole of glucose. And researchers have seen that, yes, fuel cell technology has the ability to achieve that. Okay, let's see how. Now, this again shows that hydrogen, by fermentation of sugar, we can get hydrogen from molasses, potato starch, glucose, sucrose, lactose, right? So about 60% hydrogen, and even biogas contains about, these biogases they're talking about from fermentation, okay? 60% hydrogen and 40% CO2, okay? They're also saying that hydrogen can also be produced by cellulose fermentation, okay? Around, this is what they're showing, from using different types of microorganisms. This is the design of, or this is the snapshot of a fermenter they are using for production of hydrogen. But usually it is seen that either it be fermentation of glucose or any type of carbohydrates, the maximum that can be obtained from 1 mole of glucose is 4 mole of hydrogen. But already it has been calculated that we can get up to 12 mole of hydrogen per mole of glucose or any type of hexose. So, like researchers, they are saying that if we can use the fuel cell as an electrolytic cell, so the microbial fuel cell, if we can use it as a microbial electrolytic cell, then we can use this technology for hydrogen production. Now, what is a microbial electrolytic cell? Let's see. Say, conventional microbial fuel cell, anode is anaerobic, cathode is aerobic, right? So the anode potential is about 300 millivolt. It is negatively charged because electrons are generated. Cathode potential is around 200 millivolt, and circuit working voltage is around 500 millivolt. Whereas the difference between a microbial fuel cell and a microbial electrolytic cell is that in microbial electrolytic cell, there is no oxygen in the anode also, in the cathode also. So the cathode potential is around 0 millivolt, and the circuit working voltage is around 410 millivolt. Okay. Now what happens when you make the cathode of a fuel cell anaerobic? Let's see. Anode is the same. This anaerobic will have the waste here, biomass waste will here. Your microbes will form your biofilm. They will oxidize the carbohydrates containing waste. You will generate protons, you will generate electrons, right? Electrons will, to the external circuit, they will reach the cathode. Protons will reach the cathode through the proton exchange membrane. But here, they won't have oxygen to undergo the reduction reaction. Why? Because we are maintaining the cathode in anaerobic condition. What happens then? This electron will accept this, this proton will accept this electron, undergo reduction and get converted to hydrogen. But to support that, they require about 250 millivolt, okay, potential. And that can be supplied, from external source. But think about hydrogen generation by electrolysis. For that, you will require around 1.8 volt to get hydrogen by electrolysis of water. But in this case, you require around 250 millivolt. In fact, I think it is less than that also. Okay, we'll see in the next slide. So this is one technology by which hydrogen can be produced utilizing microbial electrolytic cell. Okay. See, I think it is 0.11 volt in theory. The voltage that is required for supporting reduction reaction of the cathode, right? So this is what it is shown here. Now, hydrogen. They're talking about hydrogen recovery. Usually, it is shown that hydrogen, the electrons, we can recover around 60 to 78% electrons, and overall hydrogen recovery is around is more than 70%. Sorry, in case of microbial fuel cell, it is around 70 to 80%, I think, right? So that gives you 2.9 mole of hydrogen per mole of acetate. Mark you, this is acetate. This is not we are not talking about glucose. Obviously, we can get glucose also. From glucose, the hydrogen production will be more. But in this, they have used acetate, okay, for hydrogen recovery. So they are getting 2.9 mole of hydrogen per mole of acetate. So as you can see here, the hydrogen recovery from glucose is 71%. But acetate, it has only 2 carbon, so it is easier, okay, for catalyzing the reduction, for catalyzing the oxidation reaction, okay, and maybe that is why the the reaction kinetics is fast. That's why they are talking about acetate. But in case of glucose, we have around 6 carbon. So, with increasing carbon, the reaction kinetics, it decreases because of this bond breaking and all issues, okay? That's why maybe the hydrogen recovery is less compared to your glucose. Sorry, compared to your acetate. Now, yeah, about that little potential that we require for hydrogen production. Okay, see, where can we get it from? We can get it from wind energy, and we can also get it by introducing this one, a solar plate. Maybe then since it's only 250 milliwatt, or maybe 114 or 110 milliwatt that is required on the cathode side. So that can be sufficed by or met by wind or solar energy. Okay, so by integrated technology, okay, this can be achieved. But if we talk about anaerobic digesters, okay, throughout the year performance, okay, is not that high. Okay, so this is a better technology compared to your anaerobic digesters. So, and another thing is that here I have here another thing that is shown is that if we now, along with on the cathodic chamber, if we introduce carbon dioxide, what will happen? We'll have protons from the anode, we'll have electrons from the external circuit, and over and above that, we will have carbon dioxide if you introduce. Or maybe if you introduce this carbon dioxide, I'll show you. This carbon dioxide, if you introduce to the cathodic chamber, what will happen? What will be the byproduct? Obviously, it will be methane. Got it? So this is how microbial fuel cells, when the cathode chamber is made anaerobic, they start performing as microbial electrolytic cells, and they can be used both for production of hydrogen as well as for production of methane, provided we introduce the byproduct of the anode, that is CO2, into the cathode. Externally also we can supply CO2, that is a different issue. Now scientists have also discovered certain microorganisms, fermentative microorganisms and methanogenic microorganisms, which work in symbiosis. One produces hydrogen or from glucose or carbohydrate containing substrates, and the other to which when CO2 is introduced, they can easily convert it into methane because they are methanogenic in nature. So this is what these are fermentative microbes which break down glucose, and these are methanogenic microorganisms which convert electrons, protons, and carbon dioxide introduced to methane. Such type of existence has been discovered. This is a SAM image. Okay, this is a fermentative microbe, and this is a methanogenic microbe. That is referred to as electron methanogenesis. Okay. So methane from electrical current using an MFC, as I already said, this will have fermentative microbe, this will have methanogens. Only you need to introduce this methane, this carbon dioxide here. So instead of hydrogen, you can get methane also as the byproduct. Okay. Apart from that, we can also use the fuel cell technology for chemical production. So electricity we know, hydrogen we know, methane we know. We can also use it for sodium hydroxide production, hydrogen peroxide, acetate, ethanol, and so on. Okay, just read this. This shows how the difference between anaerobic digestion technology and the microbial fuel cell technology. It's a bit blurred, but it shows that fuel cell technology is better than your anaerobic digestion technology. Okay. Scaling up, as I already said, there is a need to scale up. We need to work on the factors, we need to work on the cathode materials, we need to work on the anode materials, we need to decrease the cost, we need to work on the architecture to actually make this technology practicable. Right? I think I'm out of time over 3:36. Okay. So this is how hydrogen fuel cells can be coupled with electrolyzers. We get power from sun. Okay. So this is the electrolyzer, this is the fuel cell. Okay. Now the electrolyzer, it will break down water into hydrogen and oxygen. So this oxygen can be diverted here to the cathode side. This is hydrogen, fuel cell, electricity generation. Fuel cell will give you water, which can be introduced in the electrolyzer. So this is the hybrid technology. If it is like it's a complete cycle system, right? It's like a water cycle system, complete cycle system of electricity generation with no waste, right? And it looks very easy, but better said than done, right? So biological fuel cell can also be used as biosensor. I'll just skip through because I have to attend. Okay. See, by using the anode itself, okay, if we can get some response, then that half cell from half cell only we can, that response can be recorded and amplified, and we can use it as a biosensor. Let me show you a simple example. Okay, see, instead of the electrode, if you give here hydrogen or mercury contaminated water. Now in contaminated water, mercury usually stays at 2+, in 2+ oxidation state. So this anaerobic chamber, which will have your anode, okay, mercury. So what happens is electron, it will reduce this mercury and it will reduce it to 0 state. So what happens, your potential will decrease. Now, if we can calibrate this, okay, then actually we can use the anode or the half cell of a fuel cell for, for as a biosensor. I'll just show simply, I just say we collected wastewater, okay, then we develop the anode surface. This is a carbon cloth where we develop the anode. So this is day 1, day 0, all white. Now we incubated in wastewater, so the electrode surface, that biofilm started forming. So this is the biofilm, JS3 and J5 biofilm. Okay, now this we can use as a sensing surface. Okay, see, and obviously since we are using a half cell, it has to have a reference electrode. Either we can use silver chloride or salt bridge as the reference electrode. Also, we'll have a counter electrode, like copper wire can act as the counter electrode. Maybe we can fabricate something like this. Okay, this is the working electrode. Okay, this is the counter electrode, copper wire, and this is a reference electrode, silver chloride. Now, day 1, day 3, day 5. See the increase in color, because these are purple non-sulfur bacteria which was present in our wastewater. Okay. So this is fresh media. With time, what happens? The potential, it increases, so it's negative. This is the growth curve of the microbes. With time, the growth also increases. That is optical density. Now, day 1, day 2, day 3. So with increase in day, the current, the voltage, it increases. Day 1, day 2, day 3. Okay. And this is, I have shown a canthaxanthin because of the presence of that red color pigment. Okay. Now see, this is from pond base. Now, when we introduce mercury into the system, from 0 mercury to presence of mercury, see, the peak, voltage peak, it was quenched. Why? Because the electrons, okay, it reduced mercury. Now, if we can actually, form a calibration of this voltage reduction, we can use this system as a biosensor for detection of mercury in water. Got it? So this is the peak we get day 4, and this is the peak on introduction of mercury, peak reduction. Got it? So in fact, pH also changes. 0 pp. This is pH is high, but with increase in mercury, pH also changes. That is another thing. If we can club this feature with that voltage reduction feature, and this is zeta potential to show that actually the presence of mercury decreases the potential, that is electrons on the potential of your system. Because what this we checked in what FESM images and XPS on XPS detection, on EDX detection, we discovered that in microbes containing microbes growing in contaminated or water containing mercury, they collect the mercury on the surface. Okay, and those mercury, the presence of those mercury shows reduction in voltage. So that was detected by zeta potential in presence of mercury. Okay, as you can see, with increase in mercury concentration, it is zeta potential decreased. So these 3 things: zeta potential decreases, the mercury is captured on the wall, electron reducing mercury ions, this from the 2+ state to 0 state, and the current output also decreases. So these factors or these characteristics we can apply for designing of a biosensor. This is the CV at different mercury concentrations, voltage, high voltage, but with increase in mercury, it is quenched because the mercury in oxidized state, okay, it accepts the electrons, gets reduced to 0 state. Okay, so that's all. Dr. Manjula, I am done with my talk.
Thank you, ma'am. It was exhaustive research that you have shown us. Thank you so much.
Okay, thank you.
And participants, if you have any question, you can ask ma'am. If you have any doubt or anything that you want to ask regarding the topic that she has discussed. Yeah, Gajananji, thank you.
Okay, thank you. Should I leave, Manjula? Can I leave?
I think no question from the
Okay.
participants. Okay, thank you so much. I'll be in
Thank
touch
you.
with you
Sure,
related
sure.
to other matter.
I have a
Thank
question.
you, ma'am. Okay, yes. I think Vasant sir is having some
One
question.
question.
Yes, yes. Hello?
See, just 1 week back,
Yes,
there was
sir.
a viral news on our WhatsApp
Okay.
that 6 potatoes can power a lamp in your house for 1 week.
Yes, sir.
Can you throw some light on that?
No, actually, sir, that starch reducing anything that can be oxidized, that not only this is not recent, sir. We have seen that by introducing, inserting rod also into your this one. But mud also you can get electricity generation. But what will be the cost, sir? What will be the cost? So we have to calculate everything because there are different ways of achieving. That is not an issue. Yes, I know that is possible, sir. By using lemon also we can generate electricity. But people have been showing, school students have been showing this. This is not very new. This has been there maybe since last 10 or 15 years. But that is not practicable, sir. I don't think so. That is possible. I'm not saying that's not possible. But is that practical? We don't want to use potato for electricity generation because already we do not want to interfere with the food chain. Right, sir? That is one thing. Obviously, it is possible because we are not targeting for biofuel. Also, we are not targeting the corn because we do not want to, interfere with the food chain. So already because there are other ways of getting it. So why we interfere with the food chain? I'm not saying it is not possible. It is possible, sir. In fact, if you see the YouTube, you will see lemons also are being used for electricity generation. That oxidation reaction takes place, electrons are generated, they use two rods, okay, sir? So zinc and copper, I think they use it. So that gets, the electricity gets, the electrons get captured, that is same as electricity. But long run, that won't be, sir, economically efficient. I don't think so, sir.
Thank you very much.
Thank you, sir. Thank you.
Thank you, ma'am.
Thank you. Thank you.
Okay.
Okay. Okay. Bye.
Okay, participants, the attendance sheet and